Hi class, today we are starting our new unit of work and energy. What we should understand by the end of this unit. We should understand what work is, how to define and calculate it, and what power is and how to define and calculate it. For this lecture, we are just going to focus on those two bullet points, work and power. What is energy? We use the word energy a lot in everyday life, but not often do we define it. So how would you define energy? In physics, we define energy as the ability to do work. To understand energy better, we need to first understand exactly what work is. Work is the product of a force exerted on an object and the distance the object moves in the direction of the force. So we have work, capital W, equals a force, and D represents the distance. And now you see the word parallel. We're going to talk about that a little bit more. So let's hold off on the word parallel for now. Work on a system will be able to increase or decrease the energy of a system. If we do work to a system, that means we can either be doing positive work and increasing the energy of the system, or we can be doing negative work and decreasing the energy of the system. What are the units for work? We know work, W, equals force times distance. Forces are measured in newtons, and displacement is measured in meters. So we see the units for work are Newton meters. We call this joules. So the unit for work is joules, and this is named after James Joule, who did a lot of research in the topic of work and energy. Let's talk a little bit more about work being positive and negative. So let's first look at positive work. We know, just like the equation said before, in order for work to be done, the force applied must be parallel to the distance moved. So first we see that the force vector and the displacement vector are parallel to each other. So here we have the force vector, and here is the displacement vector, and they're both parallel to each other. This is positive work because the force and displacement are in the same direction. So we see the force is pointed in the positive direction to the right. The displacement is also pointed in the positive direction to the right. So we know they are both in the same direction, so the work done will be positive. Positive work, as we said before, will increase the energy of a system. Now let's look at negative work. In order for negative work to be done, the force applied must be parallel to the distance moved. So even though these two vectors, the displacement vector and the force vector, are not pointed in the same direction, they are still parallel to one another. So we know right here that there is work going to be done. This work will be negative because the force and the displacement vectors are in opposite directions. We see the displacement vector is pointed towards the positive side or to the right, and the force vector is pointed to the left or the negative side. So this negative work, it would decrease the energy of a system. Now let's look at a case when there is no work being done. If the force applied is perpendicular to the displacement vector, there will be no work done. So here I have the force vector pointed upwards and the displacement vector pointed to the right. We see they make a 90-degree angle between them both. So right here we know that the two vectors are perpendicular and there will be no work done to the system. If there is no work done to the system, this will result in no change of energy of the system. Now let's look at an example problem with work. What is the work done by 5 Newton force applied over a distance of 1 meter? So I will let you guys try this problem. Now let's look at the work required to lift an object upwards. When we talk about the work to lift an object upwards, we assume that the object is lifted at constant velocity. That means the acceleration is 0. Now this is a very important point. If we're talking about the force required, then we need to lift a box or a certain object up, we're going to assume that that acceleration is 0. If the acceleration is 0, we can say sigma f equals ma. From here we can do sigma f equals m times 0 for the acceleration. So then we see once we move the force of gravity over, we can add it to both sides. We see that force applied is equal to the force of gravity, which is equal to mg. So to move an object upwards at constant velocity, that force applied will be equal to mg, or the force of gravity. Let's look at the work done by a force acting at an angle. Not often when we apply a force to an object is the force directly horizontal or it's directly vertical. A lot of the times we apply a force at an angle. So here we have a woman applying a force through tension in the string on a block, and we see that force is an angle theta above the horizontal. So now we are able to say that work equals the force times the distance times the cosine of theta. So in the next slide we're going to dive in a little bit deeper as to how we got this equation. So what we're looking for is we're trying to find the work done by that force when it's acting on an angle. We see the displacement is horizontal to the right. Let's call this along the x-axis, and we'll call anything going up and down along the y-axis. So when we look at this force, we see part of the force acts up and down along the y, and another part of the force acts left and right towards or along the x-axis. So when we see that part of the force that acts upwards along the y, that part of the force is perpendicular to the displacement, so that part of the force will not do any work on the object. But here we see the part of the force going along the x-axis. That part of the force is parallel to the displacement, so this part of the force will do work on the object. So the amount of force acting on the object that will cause work done will be only equal to F cosine of theta. That will give us this portion, the horizontal portion of the force. Let's try an example problem to calculate the work done with a force at an angle. A woman moves a crate 4 meters by applying a 50 Newton force at an angle theta equals 30 degrees above the horizontal. How much work does she do? I will let you guys try this problem on your own. If we look at a force versus displacement graph where we have force on the y and displacement along the x, we see the area underneath the curve will represent the work done. Let's first look at the work in this red shaded area. We see this shape is a square, so the work done, or area under the curve, will be equal to the base, which is 5, times the height, which is also 5, so that will get us 25 joules. If we look at the work done in the green area, we see how this forms a triangle, so the work done will be equal to 1/2 the base times the height. We get a total area or work of 12.5 joules. So the total work underneath this whole entire curve, it'll be equal to 25 plus 12.5, and we get 37.5 joules. Now let's talk about power. Power is defined as the rate in which work is done. We often see light bulbs with ratings like 60 watts, 100 watts, 40 watts. What do those ratings mean? Well, they're a measurement of the power of the light bulb. So a 100-watt light bulb will convert 100 joules of energy into light and heat every second. A 40-watt light bulb will only convert 40 joules of energy every second. Remember, we defined power as the rate in which work is done. So we can say power, or capital P, equals capital W, the work, divided by lowercase t, the time. We know work is equal to the force times the distance, so we can also say power is equal to force times distance divided by the time. And we see if the force is acting at an angle, we know that force will be equal to F cosine of theta. So we can also say power equals force times distance times the cosine of theta divided by lowercase t, the time. Remember, power is measured in watts, work is measured in joules, and time is measured in seconds. Calculating power with a constant velocity. We can also calculate power by a force and a constant velocity. So let's look back to our equation. We know power equals work divided by the time. We can substitute in force times distance for work. And now we see, when we split this up, we see it equals to force times the distance divided by time. And that distance divided by time, that's the same as the velocity. So you can also say power equals force times velocity. Now this velocity and the force, they must be parallel to each other. If they are not parallel to each other, there will be no work done, and therefore no power. Let's try an example problem to calculate the power. A horse exerts a force of 800 newtons on a buggy over a distance of 20 meters in 21.47 seconds. How much power does the horse exert? I will let you guys try this problem. Let's take a quick look at what we learned today. Work equals force times distance. You might hear us call this also displacement. If the force applied to an object is at an angle, we are only looking for the part of the force which is parallel to the displacement. Power is the rate in which work is done. We calculate it by the work divided by the time. And we can also calculate power by the force applied times the velocity of the object. Coming up next, we will do some practice problems, work on a power lab, and then talk about some different forms of energy.